Buongiorno ragazzi. Allora, last time Roberto Cavicchioli, I think introduced you guys to the P threads, right? Doing some first practical examples. So make sure you're able to run these kind of first examples, as they will be needed for you guys to train on the written exam. So the best thing to try and solve the exercises that I will give you throughout the course is to write the code, make it run, printing out whatever the concurrent threads print, okay, and interleave in their execution. And this is the best guarantee to see whether what you designed works properly and accordingly to the specification, okay? So if you need any help, feel free to bug me or Roberto about these kind of problems, okay? So in the first classes, we introduced concurrency, synchronization, okay? We will go back to that in later lessons, later classes. We will do more exercises, of course. We talked about the shared memory system. I will spend a few words also on message passing systems. But yes, we will make sure to exercise a lot on this kind of synchronization and mutual exclusion problems, okay? But now I would like, I'm eager to start also the most theoretical part on real-time systems. So on real-time scheduling and schedulability analysis, okay? For this part, the reference book is Giorgio Buttazzo's book. Again, you don't need to buy it. You don't need to buy it, okay? If you need a reference, that's the reference to use. The first introductory class I will give today provides you with some terminologies, nomenclature, okay, assumptions that we do to schematize the behavior of recurring real-time activities, okay? In the first class we mentioned what do we mean with the real-time embedded system, with a real-time system, okay? We also showed some examples like an inverted pendulum, and we showed how like a delayed computation, a delayed control loop may affect the stability of such a system, okay? So it is not just a matter of designing efficient control applications. So it's not just an automation problem, something that you probably studied in the Controlli Automatici course, okay? Automated control courses, those of you which come from engineering. So it is not just a matter of writing control equations, controllers. It's also a matter on how to implement the control tasks on a real-time operating system. So the way these control tasks respond, so they compute whatever is needed from an input sensing parameter to an output actuation, so the delay you have from sensing to actuation significantly influence control stability and performance, okay? Again, this course is not on control, that's another course on control, having more to do with MATLAB, Simulink, or whatever kind of simulation tool you would like to use. This is more to how to implement control tasks to a real embedded system, okay? And so now let's delve a little bit more into this kind of tasks. How are they made, okay? So a task is essentially for us, it's like a synonymous, like it's the same thing as a thread for us. So it's a sequence of instruction, okay, a sequence of instructions that is executed until completion, okay? It's a sequence of instruction that our thread or process or whatsoever executes until it completes, okay? So you can just imagine our tasks as executing one instruction after another, okay? They can be go to memory, they can be add, multiply, control loops, whatever, okay? it may be interrupted by some other task. Okay, so we are dealing with concurrent systems. Okay, so we have multiple tasks executing together. Again, it can be process or a thread. Okay, depending on the operating system that you use. But what we focus at is the execution flow. Okay, it's more a thread concept than a process concept. So it's more not like the ownership of resources, but rather the execution flow. So what do we schedule is execution flow. Our execution flows. Okay, so how do they compete for accessing the processor, the processing bandwidth? Okay, so for now we will just focus on scheduling the processor. Okay, you could also schedule other resources. We will see we could also do policies, scheduling policies for shared resources. What is a shared resources? You know it, right, from the first classes. It may be a shared data structure. It may be an I/O device, okay? We could also schedule the access to the shared resources, okay? But for now, we are just concerned with the scheduling of the core, okay? And for now, we will just assume a single core, okay? In other course that I'm giving in the other department, we are talking about multiple cores, okay? But for now, here in this course, we will assume we have a single core, okay? And try to understand how do we schedule it. Okay, so this is our task, okay? A task sooner or later arrives, okay? And sooner or later it gets executed. Note that arriving time and starting time are two different things. So arrival time, we said it already, arrival time is when the task is put into the ready queue, okay? So where the operating system, where the scheduler may take it and put it to execution, okay? But these two instances may be separated, okay? If the scheduler decides to execute other tasks instead, okay? So arrival time, we typically denote the arrival time with an up arrow, okay? With an up arrow is the arrival time of our task. It means that from this moment on, the task is eligible to be scheduled. Okay, the task is eligible to be scheduled. It is not scheduled, okay, but it is eligible to be scheduled. It could be scheduled right away, but for instance, in this case, it is not. So it is scheduled a little bit later at its start time. Okay, start time is the time when the task is scheduled. Okay, so the first time when the task is scheduled is the start time. When the task completes, is called finishing time. Okay. So here we see an uninterrupted execution flow. So the task is scheduled at some point and it executes continuously until its end. This may not always be the case when the task is preempted or the task blocks on a shared variable, okay, on a condition variable or whatever, okay. So this is the notion of a general task. General task, not a real-time task. This is a general task. Whatever task you have in your laptop or in your application, it's again something that arrives at some point and gets scheduled at some other point. It executes and it finishes. Okay, that's a very basic, simple thing ever. Okay, so this is the state transition that we are focused on. We already saw the more complex one, so this is a simplified one. So when a task is activated, so the up arrow, it gets into the ready state, okay? It is eligible to be scheduled. It is eligible to be executed, okay? When it is executed, we call it dispatching. So this is the start time, okay? The first time it gets dispatched, it is the start time, okay? Then it may be preempted by other tasks and go back to the ready queue and rescheduled again, okay? You can do that multiple times. Every time you do a switch is a context switch, okay? This is either a preemption or it may be a blocking condition, okay? So a running task maybe encounters a condition variable or a semaphore or a mutex or whatsoever. It is not able to access it, then we know it is suspended, okay? It blocks, okay? So it relinquishes the processor, it relinquishes the core and leave it to someone else, okay, while it goes into a blocking queue. Okay? So from this blocking queue, who is responsible to wake him up? Some other executing tasks for I/O, interrupt or whatsoever. Okay? Some other task or interrupt or whoever will sooner or later will eventually wake him up and put it back on the ready queue. Okay? This is the very basic, simple scheme transition diagram. We will call a task active whenever it is either in the ready or running state. So in this case, the task is active. Okay? It is either eligible to be executed or it is executing. Okay? When it is blocked, it is not eligible to be executed. Okay? Okay, so we said that the tasks that have arrived and that are not blocked are put into a ready queue. Okay, so we can assume our ready queue is a simple queue which may be sorted according to some algorithm, to some sorting algorithm. Okay, for now we can just assume a first in, first out queue. Okay, so the first one that arrives is on top, the last one that arrived is at the back of the queue. Okay, and the guy, the component that decides which one to schedule is the scheduler, and the policy according to which the scheduler decides which guy to schedule is called scheduling algorithm. Okay, so the policy according to which the operating system, namely the scheduler components, decide which one to take from the ready queue and dispatch to the processor, it is called scheduling algorithm. Okay? We will see a few scheduling algorithms. Fixed priority, rate monotonic, earliest deadline first, and so on. Okay? So the ready queue is an important component because it basically stores all tasks that are eligible to be scheduled. So how can this scheduling algorithm be implemented? So a first distinction between, first categorization between a scheduling algorithm is between preemptive and non-preemptive. Okay? Remember in the first slide I showed you there was a task starting and executing uninterruptedly until its end. Okay? If no task can ever be interrupted during execution, this policy is called non-preemptive. Okay, so the task that runs cannot be interrupted, suspended, or whatsoever until the end of its execution. Okay? Policies that implement this kind of thing are called non-preemptive policies. Okay? They have pros and cons. Okay? On one side, the task finishes earlier after its starting time. On the other side, this task, since it is not interruptible, it may add some blocking, it may delay the computation of higher priority tasks, which is something that may harm critical activities. We will see it better in detail, but again, let me repeat it. If we use a non-preemptive system, like the execution of a lower priority task, which just monopolizes the processor for a long time, may be detrimental to critical activities that need a prompter interaction. Okay? So if I have a guy that just executes continuously without possibly being interrupted, okay, then this may cause significant delay to more critical activities. Okay? This is something that we typically try to avoid in real-time scheduling. So the contrary is a preemptive system, and that means that a running task can be interrupted, can be preempted, and some other tasks, potentially more critical activities, can execute instead. Okay? So this guy can be interrupted at any time as soon as, like, for instance, a higher priority activity arrives. Then these high priority activities take the processor. Okay? They are more urgent. When they're done, the preempted one may continue executing. So these policies are called preemptive policies. Okay? So they require some more support because you probably guessed that preemptive policies require some more context switch support. So whenever I interrupt a task and I execute someone else instead, I do a context switch. I need to save registers, variables, okay, stack, memory, need to store that to memory, and when it resumes execution, I need to pop back all these register, variables, whatever, for the executing task. Okay? So this requires additional support. On the other side, it is much more reactive, it is much more promptly answering to critical activities that need to urgently access the processors. Okay? So that's a very simple nomenclature. So how do we define a schedule? So a schedule is a particular assignment of these activities, these tasks, to cores, okay, to one or more cores. Again, we will assume for now having a single core. Okay, so a schedule is just a particular function that assigns for every time instant a particular task to be executed on the single core available. Okay, so this is a task set. Okay, so I have multiple tasks. Okay, task set, we call it either with a big T, this is a gamma. So it is composed by typically n different tasks. Okay, ta1, ta10. And what does a schedule do? So a schedule is essentially a mapping function. I called it sigma of t, that maps every time instant, okay, in the real domain. Okay, so every time instance, it maps such an instant to a given task index. So if I have n tasks, at time 1, these will be assigned to task 3. At time 2, task 3. At time 4, task 3. And time 5, task 1. Okay, so this is like a basic definition for a schedule. Okay, so we will say that the sigma t function, if equals, so the index of the task that is running, okay, otherwise if no task is running, for instance there is no task ready, there is no task active, then we will assign it a 0, okay? So the scheduling function is a 0, is null whenever the processor is idle, so no tasks execute, okay? This is a sample, like a simple example of a schedule function. So we have 3 tasks. I decide first to schedule task 1. So the schedule function goes to 1. At some point I want to schedule 2. At some point I want to schedule 3. And then my processor goes back in an idle state. Okay? It's a very simple stepwise function. Okay? So we have a context switch times. So this is a context switch, this is a context switch, this is a context switch, and this is again a context switch, okay? So you may wonder what kind of a context switch is this one or this one. So this is from operating system to task scheduling, and this is from a task to an operating system back, okay? The idle task, either I have an idle task, or I do just leave the operating system on, okay? Operating system, you may know, is just an endless loop, okay? It's just something that executes constantly. It may go to sleep mode, but still, it is awake. Each interval, each scheduling interval is called a time slice. Okay, I call that a time slice. Time slice, time slice. So that was for general tasks, okay? Not real-time tasks, general tasks, okay? What if I introduce real-time tasks? In the first class, we said what was a real-time task. A real-time task is basically an activity for which we do not just care about the functional correctness, but also about the timing. So when it completes execution. Okay? So real-time task is not just something that needs to execute, but it is something that needs to execute before a given deadline. Okay? So, brilliant idea, we just add a deadline here. Okay? So, we have the general task model with arrival time, start time, finishing time. Typically the amount of execution is called execution time. Okay? Execution time. So it's the amount of execution, it's the amount of processing time that that task requires. Okay? We call it execution time. In real-time systems, we are not concerned, I told you, about average performance. Okay? What do we care about in real-time system, if not on average? On? You can tell it in Italian if you don't know. So real-time systems are not concerned about average performance, but about, no one? Worst case. Okay? Worst case is also written there. Okay? So real-time system, worst case performance. Okay? We are concerned of whatever can happen in the worst case possible. Okay? So real-time systems, just to remind you, are concerned with the Murphy's law. Okay? If something may go wrong, it will go wrong. Okay? So this is the most important thing for real-time system. If you need to qualify for ISO compliance, your automotive system, you need to prove that whatever thing may happen, your task is safe and robust. It will compute everything in time. Okay? So you're not much concerned about execution time. You are concerned about worst case execution time. Okay? So for us, the execution time, the CI that we say here, that we see here, the CI, it will be always the worst case execution time. Not the average, not the best, not just a random sampling of the execution time. It is the worst case execution time. Okay? This may be connected to the problem of deriving the worst case execution time. Okay? We call it WCET. Okay? This is like a common terminology in the real-time literature. So WCET, worst case execution time. How do we compute the worst case execution time? The answer is, it is a mess. It is difficult to compute the worst case execution time. Can you guess why?
Because we have event that can block the run.
This is one reason. Other reasons?
The resource.
The source is another reason. Also, even for tasks that do not access resources, not even a single task that executes alone. How are these? When you program a task, it is just like a sequence of instructions, or like the control flow may jump from one part to another one. You may have while loop with undetermined control variable, while n greater than 0, and this n depends on a lot of things. You may have if then else's, right? You may have control loops. You may have a lot of control stat, jumps, conditional execution, and stuff like that, that affect what kind of instruction will be executed, right? So if I run my task 100 times, who ensures me, even without any interfering task, okay? I'm the only task executing, okay? If I'm running 100 times, who assures me that I identified the worst case situation, okay? I told you, simulating a system, running it multiple times, it is not a proper guarantee that that is your worst case, okay? It is not a sufficient guarantee, okay? So of course we do that. We do that because we don't want always to analyze deeply every kind of task system. So I'm digressing a little bit from the slide here because this is like an important concept, I guess, for you guys, okay? So finding this WCET is something that is difficult because, again, our task may be schematized as a lot of conditional branches, dependencies. You may have while loops that depend on variable which are modified during the task code. Okay, so simulating it multiple times, it doesn't assure you that you identified the worst case path ever. Okay, so in this sense, since deriving this WCET, it's a very important thing. What the industry does is either still running it hundreds, millions of times and adding some margin on top of it, but still this is not a safe assumption, or using WCET analysis tool that mathematically try to explore the tree of all possible execution flows that you may experience in a given task. Okay? So you try to explore all possible execution flow with an engine, with a software, with a tool, okay, a very complex tool, okay, that is able, with exponential complexity typically, to identify what is the worst case ever that may arise in that system and gives you back the worst case execution time. Okay? So these analytical tools are the only way to provide an analytical guarantee that the WCT is CI. Okay? Without that tools, since using that tools is either expensive or very too much overly time consuming and so on, what we do, yes, we still recur to simulations, so to running it multiple times and adding some margin. Again, this is not like the best thing you can do. It is not an analytical guarantee. It's just like a quick and dirty way that industry adopts to avoid delving into such a complex problem. Okay? On another side, what we may do to simplify the WCT derivation is writing code properly. What do I mean with properly? So in real-time systems, there are some kind of guidelines, unwritten rules, suggestions, recommendations that specify how to write a code so that it will be predictable. So, for instance, avoid unbounded loops. Okay, if you need to do loop, you can do loop, of course, you can do whiles and for, just use a bounded number of cycles. So do not use a while like as a control variable in a while, do not use like a variable that is modified dynamically. You can do instead while I is less than 1000, then you know that you will do this cycle exactly 1000 way. But do not use like I less than n, where n is modified dynamically. Then it will be a mess to identify what is the largest n, what is the largest number of iterations that you can do. Okay? Other things, you try to limit the use of pointers. Try to limit the use of pointers. You know that using pointers may expose you to problems. Okay? Maybe there is not space to allocate them. Maybe there are some pointer chasing problems. So there are multiple guidelines. In the automotive community, typically code is tentatively written in a MISRA-C compliant way. So MISRA-C compliant is a set of guidelines for you to write code that may result in the application, in the task, being more predictable. Okay, so it does this kind of limited use of pointer, limited, bounded loops, and so on. Okay. Okay, so going back here, deriving the CI, it's a very important thing. Okay, it's a very important thing. When you are in a single core with this kind of techniques, at the end you can do that. When you go to a multi-core, this is part of the research we are doing as a lab. When you're doing that for a multi-core, so deriving this guy here, this CI, it's a very difficult task because then you have a lot of interdependencies of cores, accessing shared memory, caches, interconnection, buses, and so on. So it really opens up to thousands of different scenarios and makes the problem of deriving CI extremely strongly NP-hard. Okay? So we are studying as a lab ways to simplify, execution model to simplify the derivation of CI also in more complex setting like multi-cores, heterogeneous architecture, GPUs, and so on. Okay? This is like probably the main research activities that we do there. Okay, so real-time task, we have a deadline. Okay, so this is like the time instant by which I would like my task to have completed execution. Okay, so this Fi, this completion time, shall be earlier than this deadline. Okay, there are a subtle difference between absolute and relative deadlines. Okay, so how do they differ? So the absolute deadline is an absolute time instant. Okay, if this is time and the beginning is 0, this task may have a deadline at 1,000 million, for instance, if time just goes on. Okay, this is the absolute deadline. So the amount of time since the origin of times by which I would like this task, this activity to have ended. The relative deadline, it's a simpler concept. It's just the difference between this absolute deadline and the arrival time. So typically it has a much shorter value, okay? So if this was 1 million and this was 1 million minus 1,000, okay? The deadline relative is 1,000, okay? So it's just the difference of time from the starting, the arrival of the task and the absolute deadline, okay? So typically we denote with the capital letters relative execution time, okay? While with a small letter, absolute execution time. So small letters are typically higher value that can go very, very long, very, very large as time goes on, okay? So this task has a release time, the next release time will be higher, the next higher, and so on, okay? The same for the starting time, finishing time, and absolute deadline. While the relative deadline is something that is typically much smaller, okay? So relative parameters are labeled with capital letters, absolute parameters with small letters, okay? Okay, let's define other meaningful parameters for a real-time system designer. So what do we care about when designing a real-time system? I told you, we care that the finishing time is earlier than the deadline, okay? We would like the task to complete before the deadline. So the difference between the deadline and the finishing time is called slack, okay? So the slack is the difference between the finishing time and the deadline, okay? So, we have like lateness, also called, like it's better called. So essentially there is a maximum with 0 that here, okay, here is the tardiness. Okay, let's go like finishing time minus deadline. So if this task completes later than the deadline, if this guy completes later than the deadline, the amount by which it completes later than the deadline is called lateness. Okay, so finishing time minus deadline is called lateness. In this case, the lateness is negative, means that the task is early, okay, it's not late. Okay, the tardiness is essentially the same as lateness, only with a maximum to 0, meaning this magnitude here tells you if the task is late, then it's a positive value. If it is not late, it is 0. Okay. So tardiness and lateness are similar concepts. So they essentially measure how late the task is. Okay? So if capital CI is the worst case execution time, at some point t, we may want to determine how much of this task is still pending to execute. So what is the remaining, the residual execution time of that task at time t. So the residual execution time of that task at time t is called small c I t. Okay, we call this residual worst case execution time. How much more that task needs to execute at time t. Okay, of course here for all instants in between here, the c small it is equal to big C I, okay, because the task did not yet execute the single instruction, okay? So the residual execution time before starting time equals the worst case execution time itself, okay? we can see it here. Okay, so we can compute the laxity or the slack at time t as well. Okay, what is the laxity that the task has here? What is the laxity that the task has here? We label the laxity as the deadline minus the time, okay, minus whatever remains to execute for that task. Again, if I'm at time t, okay, how much slack do I have for that task to complete execution? So the slack is this minus the remaining time, okay? This is di minus di, this is di minus di, minus ci, okay? And this is the slack, which can be computed at every time t, okay? Okay? Then, for now, it was just for one single instance of a task. One single arrival, one single execution, one single deadline, okay? But I told you that real-time systems are very, very often recurring activities, okay? They repeat themselves every period, okay? Either with a periodic, strictly periodic behavior, or aperiodic or sporadic behavior, okay? So, but they are essentially recurring activities. We are not interested in just scheduling a batch application, like in a simulation, right? We run it, it's over, we are done. No, here we would like to schedule concurrent tasks that repeat themselves with different periods, okay? This is essentially real-time scheduling, okay? Remember the example that we gave. I have like an autonomous cars. It had like the sensor for, I don't know, the camera, the sensor for the radar, like a task that does sensor fusion, another task that which has much smaller period does the control of the actuators, okay? It may be that our system has multiple tasks with multiple different periods, okay? And we would like to make sure that all of them acquire the processor, gets executed in the single processor in a prompt way. Well, a prompt means such that all of them meet their deadlines, okay? No one of them executes after the deadline. So this is the essential scheduling prompt. So a task is not just one single instance then, but a task is a set of subsequent instances. So it is essentially an infinite sequence of jobs, okay, that recurringly executes. Again, a task is not just one job. This is called a job. Okay, one instance is called a job, but a task is the set, okay, the union of all the jobs that repeat themselves, okay, at either regular or aperiodic intervals. Okay, so that's a task for me. Okay. So job 1 is the first job that is released by that task, okay? Job K is the kth job, maybe after K period, okay? K plus 1, and so on. Note that all these jobs have different absolute deadline, but the same relative deadline. Okay, let me explain again. We have different absolute. This is maybe at time 10, 1,000, 1,010, and so on. While this guy has a relative deadline of 10, these guys have a relative deadline of 10, these guys have a relative of 10. Okay, so relative deadline are the same for all jobs composing a task. Absolute deadline keep increasing because they are absolute variables. Okay, all of them typically have the same worst case execution time, so the CI is the same as here, as here. So what does it mean here? This guy has been preempted, okay, and then continue executing. So the CI here is just the sum of this block plus this block. This is still CI, okay? Okay, what happens if I miss a deadline? I said a deadline is like the maximum amount of time at which I'm allowed to finish the execution. So I cannot finish my execution after the deadline. But the question is, what happens if a task executes after the deadline? So the effect that a deadline miss, defines what kind of task criticality do we have. So for tasks that are definitely not allowed ever to miss a deadline, these are called hard real-time tasks. So a hard real-time task is a task that simply cannot ever miss a deadline, okay? So these are hard real-time tasks, okay? Missing a deadline may have very serious consequences, okay? A car may be out of control and crash. A nuclear power nuclear reactor controller may lead to an unstable situation. An avionic autopilot may have some dangerous risks, and so on, okay? There are many cases of hard real-time systems, automotive, avionic, industrial automation, you name it, okay? Simply a task cannot miss that deadline, okay? While in some control problems, it is not a big issue if we sporadically miss some deadline. Okay, in that case, these are called firm tasks. So only a limited number of jobs. Maybe I allow one job every 10 to miss a deadline. Okay, so if this still maintains my control performances, then I'm okay. If I have 2 tasks missing a deadline, then it becomes a problem. Okay, so every k tasks, I allow n of them to miss the deadline. Okay? This is called typically a firm real-time task model. The weaker real-time notion is, yes, I still have the deadlines, but these are just suggestions. Okay? So this is soft real-time model. Okay? For instance, you would like to obtain a particular video decoding and coding quality. Okay? So you may miss a frame from time to time, or a multiple frame in a row, so the quality perceived will be degraded, but no one will die. Okay? So this is like a soft real-time task. If for you instead, it is very application dependent, because there may be application where the customer requires you to never miss a frame. Okay? It can be the same application, but with soft real-time requirements or hard real-time requirements. So if I mandate that my frames can never be missed, then it becomes a hard real-time application, okay? So it essentially depends on your customer requirements, okay? If there is not a big issue for your customer that you miss a frame from time to time, then that's a soft real-time system. If instead missing a frame or missing like a control loop from even once may arise to very dangerous consequences, or like missing your qualification application, okay, then that's a hard real-time system, okay? It essentially depends on your customer or application requirements. In Linux, essentially, almost everything is soft, okay? You could use Linux for hard real-time activities at your own danger, okay, because there are some latencies implied by a lot of the activities performed by the operating system behind, under the hood. Okay, so if we are more concerned in this course about hard real-time systems, okay? So for instance, a lot of the electronics that you have in your car, it's a hard real-time system. The engine controller cannot miss deadlines, the steering equation, the chassis signals, alarms, etc., all shall be qualified at ASIL high level. Okay, so these typically are automotive safety integrity level. High integrity level means that you need to provide strong grounds, okay, about your task meeting a deadline. Typical hard real-time tasks are, for instance, again, it depends on the application, but if I have an autonomous car, what happens if I miss a frame, like an acquisition, okay? My car gets blind, okay, for that time frame. Is this okay? Is this robust? Then it's not a hard real-time task. If this may have serious consequences, then this becomes a hard real-time task. Low-level control, this is more often a hard real-time task. Again, my motors, my electronic braking system, okay, can never miss a deadline, or can never have like a late result, okay, sensory motor planning, and so on. for enforcing real-time tasks, hard real-time activities, I told you, it is not sufficient to use Linux in most of the case, but you require a special operating system called real-time operating system, RTOS, RTOS, okay, real-time operating system. And that's called a hard real-time system. Typical soft task, I read something from the keyboard, I need some user common interpretation, it gets a little bit delayed, no one dies, some display message which are not mandatory, graphical activities. Display message is not a soft real-time task in automotive. For instance, you require for your cluster, if you use like not a physical mechanical cluster but you use a digital one, it is required to maintain at least a frame rate, I think to remember about 30 Hertz, okay, 30 frames per second. So, and that's hard, otherwise your application is not qualifiable, okay. Infotainment system are an example of soft real-time task, okay. Activation modes. I told you, we are concerned about periodic, recurring activities, okay. So who will activate, who will define the clock at which I activate the next job, the next instance? So it may be time-driven or it may be event-driven, okay? So in a time-driven setting, I have some kind of a timer that essentially tells me when to wake up that task again. So I release new jobs at regular time slots, okay? So the kernel at regular intervals releases like new jobs for my periodic task, okay? That's a strictly periodic task model, okay? So every new job, every new instance is released exactly one timer period after the previous one, okay? This is a strictly periodic task model. Instead, I may have something different. I may have tasks released by other tasks activities or from some external event, okay, or to some engine condition that arrives, okay, or to some, you name it. So to some event, okay, which are not regular timers, and that's called event-driven activation, okay. In an event-driven activation, the task is activated upon the arrival of an event, okay, or thanks to some other task that activate that task. I can have tasks activating other tasks, okay? If you did your first exercises on p-threads, you created your threads, okay? So that was a task creating other tasks, okay? So it was not a timer that fires and create with an inter-service routine a new task. You created in the main loop, or you could create a task from another task and activate it and so on, okay? So task activation may be defined in very many different ways in an event-driven environment, okay? So typically I may have tasks that are created and terminate and then are recreated and terminated by someone else and so on. Or I may have like an endless loop. I showed you, I think, an example where a task is created and after a while it gets in sleep mode, okay? It gets in sleep mode, okay? And then I return back up. So when someone wakes me up from the sleep mode, it's kind of a new activation. The task never died, okay? It was just blocked, okay? But we have this wake-up activation which can be modeled at event-driven activation, okay? Questions here? Everything's clear? Okay. So, in the periodic task model, I told you that we have jobs repeating themselves at regular intervals. So, my task model, task y, is characterized by worst case execution time, period, ti, and relative deadline. Worst case execution time, period, and relative deadline. So, this is my first instance that will be repeated after one period, ti. So from here to here is ti, okay, you see it here, ti. And it shall complete its execution by its deadline. How do I compute this deadline? Arrival time plus relative deadline. So your deadline, absolute deadline, is computed as arrival time of that task For instance, this is RI1, meaning the first instance of task 1, okay? Its absolute deadline is computed as RI1 plus the relative deadline, okay? For each one of those later jobs, the relative deadline is computed as the arrival time of that job plus the relative deadline, okay? It's an easy way to get the absolute deadline. We often have deadline relative equal to the period. Yes?
This question.
Yeah.
Why do we need an absolute deadline?
Well, you can do without it if you don't need it, but for instance, some schedulers use the absolute deadline. For instance, the EDF scheduler does not use a relative deadline, it uses absolute deadline. For instance, I need to know which kind of task to execute first based on the absolute deadline. So the one that is most urgent, okay? For instance, if I have two tasks, if I have one task that arrives here and has a deadline here, okay, and I have another task which has a deadline here, okay, and I'm here, and I'm at time t, okay, I'm at time t, and both tasks, okay, tau 1 and tau 2, both of them at time t still have some pending work to execute, okay? So, which one do I execute first, okay? I can base my scheduling decision on multiple things, okay? The first one that arrived, whatsoever. So, two different policies may be based on deadline. One is called deadline monotonic, and another one is called earliest deadline first, okay? I'm introducing things that I will repeat later in other slides, but just to answer your question. So this deadline monotonics takes into account the relative deadline, while EDF takes into account the absolute deadline, okay? So just to make you understand, what is the relative deadline? This is the relative deadline which is smaller than the relative deadline of this guy here, okay? So they essentially try to schedule first the guy with smallest deadline, either relative or absolute. So with deadline monotonic, I will first schedule this guy here, okay? And then this other guy here. With EDF, the earliest absolute deadline is this one, okay? So I will schedule first this one and then this one. EDF is probably better. Why? Because this guy is more urgent. Despite it has a larger relative deadline, it has an earlier absolute deadline. So if I instead had executed this guy instead, then this guy here would have missed his deadline, okay? While with EDF, this guy would have executed first, and these other guys would have had time to complete before his deadline, okay? So you may base your decision based on absolute deadline or relative deadlines, okay? You may base it on whatever you want, okay? Just using absolute deadline, we will show, will lead to the best strategy that you can ever apply, okay? Okay, so the task arrival, we call it phi, is the first time that this sequence of jobs arrives, okay? So this is the first time, so Ri1 equals to the task arrival, okay? The task arrives just once and then it repeats periodically, okay? So this is phi, and the later instances are just the previous release time plus the period, plus the period, plus the period, and so on. What we have here, that, yes, it's essentially the same thing, and this I already said. Okay? Other questions on that model? This is the periodic, strictly periodic task model. Okay? We also have more general models. So when we are not forced to activate each job of a task exactly at its period, we may have other kind of systems which are aperiodic system or sporadic task systems. Okay? So in an aperiodic task system, what we essentially guarantee is that the next job activation, not probably this one, but the next job activation comes later than the previous one. Okay? You don't know how much they will be spaced, the one with respect to each other, but you just know that the next one will be later. Okay? This is like the more general one, if you want. Okay? I just know that the next instance will be later than this one. I don't know anything about inter-arrival times of such job instances. So it is not a periodic one. Then there is a mix between strictly periodic and just aperiodic, which is often used, and it is called sporadic task system. So what is a sporadic task system? So for a periodic, we had this relation with an equality here. We had an equal here. In the periodic, we had that the next activation is exactly spaced by the period from the previous one. In a sporadic model, this is a greater than or equal. Greater than or equal. What do I mean? That Ti is not exactly the period at which I activate the next instance, but it is the minimum inter-arrival time. So the next, if this is my instance, the next one will be activated at least Ti later than this, or here, or here, or here, or later than that, okay? So you can see it here. So this guy arrives, the next one is here, so maybe my inter-arrival time was this. The next one may be even later than that, but it could never be earlier than that, okay? So this is a sporadic task model, okay? So Ti is not exactly the period, but it is the minimum inter-arrival time, okay? I allow my task to arrive at least Ti later than the previous instance. Did I make my point? Okay.
Can you repeat the difference
Yes.
of sporadic and periodic?
Yes, I will better show it on the board. So in a periodic, just very simply, every next activation is exactly spaced by Ti. So this is a periodic. So the next one is Ti away, the next one is Ti away, and so on. In a sporadic, the next one may happen maybe here, or may happen here, 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 but can never happen here. Did I make my point? So Ti is the minimum inter-arrival time. It will never be less than that. It could be higher than that. So the next one can even arrive here, okay? That's compliant with the sporadic task model, okay? For instance, when this happens, if you're waiting if you're waiting an external event, but you just know that event cannot be so frequent, but it can happen or never happen, okay? Then you're opposed to this kind of model. So you know that you have a minimal inter-arrival time, so you don't need to allocate a lot of bandwidth to that application because it cannot arrive so often, okay? But it may even not arrive, okay? So it may arrive even later or never, okay? So these are called sporadic task systems. So if that event never arrives, that's a sporadic task model. Okay, clear? More question?
Yes.
Yeah.
But if it arrives so late,
Yes, here?
the next reference will be much...
This one, no.
Yeah.
It will again this one. So then the later one will be at least here, cannot be here. The later one will be here or later. Okay, so this is the new reference. The arrival is this one now. Is this your question or?
I'm not sure.
So this essentially, this is your reference is the previous instance, not the previous of the previous. Okay, so this one is your previous. And for the next one, this one is your previous. So the next one will space at least Ti, can never be earlier than that. Okay.
It seems to be incremental. I don't know.
Yeah, it is.
Okay.
It is. Yes. Because I mean, what you need to take into account is the temporary load that you may have due to that task. If it never arrives for 2 hours, and then you have like constantly arriving very regular one, then that's what interests to you. Okay. So it is like the reference to the previous one that may provide you a burst of activities to execute even in a periodic way, but not more periodically than the minimal interval time. Okay. Actually, this sporadic is a very much used model, okay? Because it can reduce to the periodic, essentially when it activates always at the minimum interval time, but it can generalize also to aperiodic activities. Okay. So what kind of timing constraints do we have in our real-time systems? Okay, you're getting used to deadline, to activation time, completion time, jitter. We did not say jitter. What is jitter? So you have different kinds of jitter. So jitter may be the activation time of a task, which may vary from period to period. It may be the starting time of that task with relation to the activation time that may vary from period to period. It may be the completion jitter that may vary from period to period, okay? So jitter essentially determines the variation of some kind of magnitude, okay, from task instance to task instance, okay? So whenever you don't have a regular behavior for all instances, then that's called jitter. We will see it maybe later. Then we may have something that we did not model yet, that can be precedence constraints. So precedence constraints, they may impose an ordering in the execution of tasks. So I may have a case in which I mandate task 1 to execute before task B, to execute before task C. You remember, right, the first exercise that we made, where we have A followed by B and then C either by D or E. This is a typical kind of precedence constraints, okay? We can model that, okay? We can model that. But these are additional constraints which are called precedence constraints, okay? Or you may have resource constraints. For instance, a shared resource that may be accessed only in mutual exclusion. You may not allow two tasks that both require the very same resource. You may not allow them to execute simultaneously on that. So they need to execute atomically on that resource. This is again a different kind of timing constraints that you may have in your system, okay? We will show how to deal with this very important problem, okay? So this is a problem that caused a lot of famous incidents, accidents, like in spatial mission or aerospace or whatsoever, okay? So resource constraint synchronization, it's a very, very big problem that you need to take into account when designing real-time systems. Again, by definition, if you're writing a concurrent concurrent application, you have multiple tasks, but they need to collaborate, right, to cooperate between each other. What does it mean cooperating? Sending data between each other, modifying the same data structure, synchronizing, right? So they are not completely independent activities, okay? So otherwise, they are not concurrent tasks of the same application, they are just two different processes, right? But if tasks need to cooperate to enforce something, they need to communicate, to synchronize, to share the resources, okay? And the way they need to access in a mutual exclusive manner this shared resource, okay, may affect your timing requirements, okay? Just assume a task, we will see example, a task that has a high priority, would like to access a critical section protected by a semaphore, but there is a very low priority task that is holding that semaphore forever, okay? This effect is called priority inversion, okay, and may lead to particularly unlucky worst case scenarios, okay? And the timing constraints can be either implicit or explicit. So if I simply, my customer or my application goal mandates that I should open a valve every 10 seconds, or I can send my position every 40 milliseconds, or I should read my camera or radar every 50 hertz, okay? So that implies that the constraint is is explicitly present in your customer specification, okay? But constraint may be even implicit, okay? So I have an autonomous car, I need to avoid an obstacle while driving at speed V, okay? No one tells me what is the correct frame rate or frequency of my computation, but I need to derive it, okay? So there are some real-time requirements. We just need to figure it out so that the cars at velocity V, at speed V, will not crash into an obstacle, okay? This is not an explicitly defined constraint, but it's like an implicit constraint that we need to figure out. Or control an inverted pendulum of height h and weight w, okay? So we don't exactly know what is the period of the control task that we saw in the initial slides. You remember, read the angle, actuate on the trolley particular force with a particular gain, okay? So what period? So how often shall I do this loop, okay? Just endless while loop forever. We saw that it's not convenient because we would just monopolize one processor for like more workload than it is needed for this system. If we use this inverted pendulum with a control loop which is weak, then that may be not sufficient for the pendulum to stay in equilibrium, okay? So again, here we implicitly need to derive what kind of control task period shall we enforce for achieving stability, okay? These are implicit timing requirements. An example of precedence constraints, like I said, like the exercise that we did, okay, we may have a task that should execute before anything of tau 2 and tau 3 starts. So this guy can only start after this guy finished, okay? And this guy can start only after tau 2 finished, okay? These are typically precedence constraints, okay? We are used to identify them with a DAG, with a directed acyclic graph, okay? What is a directed acyclic graph? It's like essentially a graph, a directed graph, which does not implement any cycles in between, okay? Within, it does not have any cycle, okay? So from one point I can reach other points, okay, with no loops, okay? We will denote as a predecessor with this kind of inequality. So we say that tau 1 is a predecessor of tau 4, okay, whenever there is a relation that needs tau 1 be finished before tau 4 starts, okay? And we say immediate predecessor, like with an arrow, if tau 1 is the last one to execute before tau 2. Okay, so there is a direct relation, direct connection between one task and the following one. I don't remember, did I show you this problem in the initial slides? No? So this is like a basic vision application, okay? It's a very high level model of what can be done with the companies that we also start to work with, okay? We know that this is like a region with a lot of industrial automation industries, companies, and essentially they are integrating vision inside their production lines. So you may have like a stereo camera that takes input from two different sensors and then does the processing and then recognizes shapes and then does some kind of actuation, okay? So this is just a very, very high level simple example, okay? So you may have an acquisition task for one camera, acquisition task for the other camera, okay? Then each one of these camera feeds can be used to detect edges, okay? Contour of your shapes, okay? We have libraries, OpenCVs and so on that can be used for that purpose, okay? Then I may use the output of the edge detection of one of the cameras to derive a shape. Okay, I don't need stereo vision to define something as a square, okay, or as a rectangle, or as a circle, or whatsoever. Okay, I may need stereo vision, so edge acquisition, to derive the displacement. Okay, so stereo camera can be used to derive the distance of a particular object from the camera itself. Okay. So there is a precedence relation. I need to complete this detection of the other one, and then I use it for computing displacement. Just an example, okay? Then, once you have the displacement, you can compute the depth of your objects, okay? So its height, its width. And then when you have the depth and the shape, then you have the object recognition, okay? Then you can recognize whether it's a small cube, a big cube, a small sphere, or whatsoever, okay? So there is a precedence graph that mandates some task to be completed before the next one. And this instead is an example of shared resources. This we already saw in the concurrency slides. So if I would like to maintain a consistent behavior of concurrently executing tasks that may modify a shared resource comprising, for instance, two variables, if I allow a task, for instance, this is a writing task, to start reading, this is like a critical section, I allow this task to get preempted by a reading task, this guy will read an inconsistent state of my shared object. So if task W wanted to write 1 and 8, and this guy either wanted to read 3-5 or 1-8, but if they interleave in this way, this guy will end up reading 1-5. Okay? So it will read the initial of the update of W and the old Y value before X will complete its overwriting. Okay? That's the typical mutual exclusion problem. So what we enforce is mutual exclusion thanks to the semaphore support or blocking support or condition variable support, mutex support that we saw in the first lessons. Okay? So we essentially may allow task W to lock this shared resource. What does it mean, locking this shared resource? That whoever would like to modify it will need to sequentialize after myself. Okay? Let's see an example. Tau R still has higher priority than tau W, so whenever this guy is ready, I prefer executing him than him. Okay? So tau W arrives, there is no R here. Okay? It starts executing. Here it requests the semaphore, for instance. Okay? It is granted the lock to that resource. Okay? It enters. It starts modifying, modify X to 1, and then the high priority task arrives. Okay? The reader arrives, starts doing his business, and at this moment it tries to start reading. Okay? At this moment it does the same weight, or the conditional weight, or the mutex lock. Okay? Is it able to lock it? Not, because it is still granted to X, which did not yet release it. Okay? Then this causes tau R to block. Okay? Tau R here blocks and relinquishes the processor to another task. In this case, the only one is tau W, which may continue execution, finishing updating the shared data structure, relinquishes back the processor to the higher priority one, which now is able to access the lock, the shared data structure. This guy here, this is a send post, okay, or an unlock, okay, mutex unlock, the instruction. So what does it cause? You remember, right? The post either increments the semaphore by 1 if no one is pending, or if there is someone pending, just unblocks it and passes the token to him, right? So this guy now can execute on the critical section. When it is over, it can continue because it has higher priority, and then gives back control to the lower priority task. Okay? Notice a tedious thing here, that due to this delay delta, which was due to the blocking of task W to task R, okay, then task R misses the deadline. Okay? So the execution time of tau R was good enough to complete before the deadline, okay? But this delay here caused him to miss its deadline. Okay? It's very important that you understand this example, because we will study multiple protocols to try and avoid this scenario whenever we can avoid it. So there are situations in which we cannot, there are others in which we can. Okay? So the synchronization of the shared data structure eventually imposed some blocking, okay, to a higher priority task that led him to miss its deadline. Okay? Is it clear? Okay. So mutual exclusion does not come for free. Okay? in a real-time perspective. Okay, let me finish with some scheduling anomalies. These are curious facts that makes you understand the importance of scheduling and not just, and deeply analyzing your system and not just recurring to intuition, okay? So I will now show you that even in counterintuitive setting, the worst case may be worse than what you thought, okay? So here are like a general task system with, these are not even recurring tasks, these are not periodic, these are just batch of workload, okay? So we have, how many? 9 tasks, 1, 2, 3, 4, 5, 6, 7, 8, 9, yes, 9 tasks with some precedence constraints. Again, I'm not even considering them periodic, okay? Just one instance of them, okay? With these periods, with these, precedence relations here, okay? Task 1 needs to execute for 3 time instant, task 2, 3, and 4 for 2 time instant each. Tau 9 for 9 time instant, but it has a precedence relation from Tau 1, so it can only start executing when this guy is over. And 5, 6, 7, and 8 can only start after Tau 4 executed, okay? Maybe they're waiting some input from him, okay? Maybe whoever knows, okay? This is the typical setting that I asked you to write in the written exam, okay? So someone needs to synchronize with someone else, so write, read whatever it writes, and so on. So we assume that the highest priority is given to the task with highest index. So whenever I can, whenever 2 tasks are ready, I prefer executing the guy with the smallest task index, okay? So Tau 1 is the highest priority task, Tau 9 is the lowest priority task, okay? And this is my schedule, okay? Now I move temporarily to a multi-processor setting, okay? Now we have a 3-core system, okay? We have a 3-core system. So what I'm showing you, so what happens here in the schedule, okay? So what do I execute? I told you, so the priority is given to the task with smallest index, okay? So I have 3 processors, I can schedule 3 tasks, okay? So 1, 2, and 3 goes and execute. No precedence constraints before them, they can freely execute, okay? What do I execute next? Okay, 4, okay? Can I execute 9? Not until I reach what? The end of Tau 1, okay? Can I schedule 9? Not until I reach the end of Tau 1. Can I schedule 5, 6, 7, 8? Not until I reach the end of 4, okay? So this is essentially your schedule. I can start executing 9 just when Tau 1 is finished, and I can execute this guy here only when this guy is finished, okay? And this is like a non-preemptive system, okay? This is a non-preemptive system. As soon as I start executing Tau 9, it will continue executing until it's end, okay? If I had a preemptive system, what would have happened here? Think a little bit about that. Fixed priority. Priority is given to lowest index one. No one? If I allow preemptions,
The task 9 would be stopped.
here, right? And I could execute what instead?
T5.
T5 is executing here, right? It's already executing T5. What could I execute here instead? 5 and 6 are already executing, right? So what can I execute then also? 7, right? Either 7 or 8. In this case, 7 has smaller index, so it would execute here 7, then 9 will be restored and complete later, right? Okay? Okay, so with a non-preemptive system and these precedence constraints, what is the completion time of my application? Okay, an application typically is a set of tasks. Okay, I call application a set of tasks. So my application would complete at time instant 12. Okay, you see, we met all precedence constraints. There is like a small idle time here in processor P3 because there was no task ready to be executed here. Okay, besides those that were executed. Okay, now What do you expect if I now have 4 processors? Would that completion time increase or decrease? I mean, I add one more server, one more processor, I would expect the completion time to decrease, right? I have something that helps me scheduling stuff, right? Let's see if this is the case. You may guess that since I'm showing you this is not the case, so that's what happens in when I have 4 processors, okay? So this is again the same task set as before, okay? So I have 1, 2, 3, and 4, which can start executing, okay? Who do I execute next? So at this point here, who are the ready tasks? So 4 is completed, I execute whoever I want, this was, right? Essentially, I try to schedule the one with smallest index, right? The next point when I need to take a decision, this is a non-preemptive, okay? So the decisions are only taken at task completion times. So is this one, okay? If I had a preemptive system, decisions are taken whenever a precedence constraint is satisfied, okay? But here only at task completion time. So when tau 1 completes, okay, I don't schedule tau 9, which is now ready, but I do schedule the one with smaller index, which is tau 8, no? And now, only now, I can schedule tau 9, okay? Completion time is 15, okay?
Because
Yeah.
why I can't execute
Here.
T9 before T8?
I could execute T9 here, okay?
Why?
But not here, right? Because the index, the priority of tau 9 is smaller, okay? We assign priority based on indexes, okay? So we have one further processor. We did not change anything else. Priorities are the same, still non-preemptive, still the same precedence constraints, just one additional resource to serve our task, but not. So we have an increased latency, okay? Counterintuitive, is it? So, other example. So let's now use shorter tasks. The graph is exactly the same, just each single task execute one less. So I'm taking out a lot of workload, right? All those that executed for 2 now execute for 1. This guy that executed for 3 now execute for 2. And this guy that executed for 4 now execute for 3. Okay? And tau 9 instead of 9 executes for 8. Okay? So I took out 9 times 1, so 9 time units. Okay? I took out 9 time units of executions. Okay? Among my tasks. What happens? Same setting as before, 3 cores, okay? 1, 2, 3, 4, it's its turn executing, right? 4, it's its turn executing because 5, 6, 7, 8 are not ready until 4 is done. Now they are ready, okay? 5, 6, 7 are ready. I now need to schedule 8 and 9, right? 8 and 9, and it's 13. Remember, it was 12, with 9 units more of all of them, okay? So it's 13 now, okay? So here we shorten tasks. So assume you have like your automotive system, you miss a deadline, okay? So naively you may say, okay, I add one more processor. No, now you miss it more. Okay, now I decrease the execution. No, now you miss it more, okay? So it's not always so intuitive, whatever you need to do. So you really need to know this kind of scheduling problems. Let's simplify it further. You may think, but it is because I have precedence constraints, right? So precedence constraints are harmful, okay? So just take it out. Take all precedence constraints out, okay? Just relinquish tasks as they are free to execute whenever they want, okay? So basically I just schedule them in index order, right? 1, 2, 3, 4, 5, 6, 7, 8, and 9. Again, 16, okay? So even more than before, okay? So it's very unpredictable whatever happens here. And this is not even starting to take into account the recurring system, which are the ones which we are interested in, right? So now let's, instead of increasing the number of processors, let's try to use a faster processor. Okay, so instead of using a processor that runs at 2 gigahertz, I use one that runs at 4 gigahertz. Okay? So it's not like before that I move from 3 processors to 4. Okay, you have the discretization of tasks that they may harm you. So let's not just now use a faster one, okay? These are toy examples. We will study better the schedulability analysis of these kind of systems. So now we have tasks that share a resource. So they share a critical section accessing a shared resource. So both of them have a critical section marked in yellow here, which try to access a shared resource, which is protected by log, semaphore, mutexes, you name it, okay? By synchronization primitives. And task 1 has a higher priority, as we are used to, and task 2 has a lower priority. So assume they arrive in this way, so tau 2 starts first, then now I have a preemptive system, so tau 1 preempts him, tau 1 starts executing, it accesses the shared resource because this guy does not have the lock on it, okay, it requires here. So this execute, releases the lock, finish executing, preemption, and okay, this guy, context switch, sorry, more than preemption, this guy continue executing, here it requires the lock, finish executing, releases the lock, okay, and everyone meets the deadline, okay. What if I now use a faster processor, okay? So now a faster processor means that everyone executes faster, so whatever took 4 now takes 2, whatever took 10 now takes 5, and so on. But we can see that if this guy is faster, it may complete this green section earlier, okay? This guy is 3 times faster, because this was 1, 2, 3, now it takes 1, okay? And this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and now it's much less, okay? It requests the resource, it locks it, it gets preempted, this guy starts executing, asks for the lock is not his, this guy blocks, okay, waits for this guy to finish executing the critical section, okay, where this guy is waking up, it executes, but it's too late, it missed the deadline, okay? So I'm in a faster system, but that faster system caused the lower priority task to lock the shared resource earlier, and that led to a dangerous blocking for the higher priority task, which now misses the deadline, okay? And this is another example, okay? Last one we see a delay. If I impose a delay, if I ask a task to suspend itself for a while, okay, I can show you that that delay does not reflect identically in the response time. So a delay of delta may lead up to a delay larger than delta. So this is the same example as before. We have 2 tasks that share synchronization on a critical section, okay? And now what I do, I try tau 1 to insert a delay. So what do I mean? Tau 1 starts executing, and at this point it suspends itself for 2 times unit, okay? For instance, it just calls a sleep for 2 time instant, okay, 2 nanoseconds. It calls a nanosleep for some kind of timing delay, okay? Since he self-suspends itself, then tau 2 may go on executing. When these 2 seconds are over, they're not seconds, 2 time instant are over, then this guy wakes up, preempts tau 2, which locked already the resource, so that when this guy requires the resource, it can no more access it. So this guy will now have to need to wait for the whole critical section of tau 2 to be executed, and then he will be able to execute, okay? Only then he will be able to execute. So a delay of 2 caused a delay of much more than 2, okay? So it is not linearly reflected in the response time of that task, okay? So, lesson learned, just to sum up what we learned today. So the tests are not enough for real-time systems. So WCT, you cannot just run it multiple times, okay? Intuitive solution do not always work, okay? Increase a processor, use a further one, use a faster one, decrease worst-case execution time, take out the present constraints. None of these solutions are proved to work, Okay, there is not any intuitive solution that could work when you need 100% guarantees for hard real-time tasks. Better not to use delays. So try always to use specific operating systems, so real-time operating systems. Do not rely on general purpose operating systems if you need hard real-time guarantees. Okay, Linux and friends are okay when you have soft real-time systems. Okay, and yeah. So the operating system is the main part which is responsible to achieve this predictability. Of course, the way you write your application is as well, but the operating system needs to have predictable tools, reduced interrupt servicing routine, reduced wake-up times, fast context switch, proper scheduling algorithm, proper protocols for accessing shared resources, semaphore support, and so on, to allow you achieving your real-time guarantees, okay? And concurrency is enforced by appropriate scheduling algorithm, which are the ones that we will study in the next lessons, synchronization protocols, which are the ones we will study in the next lessons, communication mechanism, and predictable internal handling, okay? That's all, folks, for today. I will see you guys next Monday. I will not see you guys. It will be Roberto that will see you guys. I will be in Germany for a conference, but Roberto will continue his work, okay? So tentatively try to bring your laptop. I'm not sure whether he will do some exercises on that, but if you can, bring your laptop because it may be needed, okay? So with me, you will see me again next Friday, okay? So Monday, Tuesday, will be Roberto having classes with you guys, okay? Have a nice weekend.
Thank you.